Are you ready? Recording? Okay, hello everybody. Welcome to CS170. Maybe first I'll start off by introducing our teaching staff. Here we have a lot of our UGSIs and GSIs. Please just stand up, say your name, what year you are, and how many times you've been on the teaching staff for 170, starting from you now. And scream.
My name is Neha. I'm a senior. I've been here.
Everybody, I'm Alessandro. I'm co-teaching with Giovanni, and you'll get to know me a little bit better once I start in the lectures from now. I hope you enjoy the course.
And I'm Jelani Nelson. More course information is at our course website, cs170.org. You can find course policies there, homework due dates, the schedule for the rest of the semester, etc. I'm not going to get into that myself. Okay. So today I'm going to get right into it. This class is about primarily algorithms. And what is an algorithm? An algorithm is just a well-defined procedure. Is this mic working properly? Can you hear me well? Okay. It's a well-defined procedure, for carrying out some computational task. Okay. So, my algorithm for the morning is, wake up when my alarm goes off, open my eyes, feed my baby his bottle, go take a shower, etc., okay? But what do we want out of our algorithms in this class? So primarily we want three things, and maybe the first one we'll always get. We want that our algorithm, first of all, halts. We want that the algorithm is correct when it halts. It gives the correct output. And we also want efficiency. And efficiency could be measured in many different ways, right? So I want time efficiency, like I want my code to run quickly. I want to get to the answer quickly. I want to be memory efficient, not use too much memory. If I have a parallel algorithm, I want to not have to use too many parallel machines. So there are some resources, some computational resources, which might be time, memory, parallelism, randomness, okay? Whatever the resource is, I want to minimize my consumption of that computational resource. And what are the kinds of computational tasks where algorithms show up? Well, we run into algorithms all the time, like Google Maps. People use Google Maps, I think, right? So what's the problem there? You're given a description of some map, of some road network, and then there are some inputs like where I am and where I want to go. And then I feed that to the algorithm, and the algorithm runs some procedure to figure out the shortest path between those places, and then returns to me that shortest path, right? So there's some algorithm that's running there, which we're going to see later in this course. Even more simply, algorithms that we all started learning in kindergarten or before, right? Arithmetic, right? I give you two numbers, and I say, add them, give me their sum, or say, give me their product, right? So today, we're going to primarily focus on algorithms for arithmetic, just as examples to display algorithmic design and thinking. And we're going to focus on addition and multiplication. So the first question is, let's say addition. The first question is, how is the input described? And there are many different, I guess, numerical systems, like Roman numerals, etc., right? Those are not super convenient necessarily to perform arithmetic. Something that's more convenient is, let's say, the Arabic numeral system, which was popularized by Al-Khwarizmi, but invented in India. And then further later popularized by Fibonacci, which we're going to talk about later and spill into Thursday. Right? But this Arabic numeral system is the thing that we're all familiar with, and it's kind of the standard today. Right? So basically the input for our addition problem is just let's say two integers, say positive integers, x and y, given each as its digits in base 10. Okay. So let's say okay, so let's think about different algorithms for addition. I'm not just going to cover one algorithm. What's the first algorithm that most people learn? Let's say the algorithm you learn when you're a child, when you first learn numbers. Yeah.
Count on your hands.
Yeah, count on your hands, right? So 5 plus 7, I'll put 5 on one hand, and then I'll just start counting 7 more and see what I get. So 1, 2, 3, 4, 5, 6, 7. So I'm at 12. Okay. And then I say it's 12. So algorithm 1 is the algorithm that's like count on your hands. And what I really mean by that is start at x and then increment y times. That's a correct algorithm, but how efficient is it? And when I talk about efficiency now, I mean, let's say, runtime efficiency. How much time does this take? So runtime, I'm going to measure that in terms of the number of digits in x and y. So let's say that x and y are each at most n digits long. Let's say the max of the two is n digits long. Or they're each exactly n digits long. If one is shorter, I can pre-pad it with zeros and pretend that it's actually n digits. So they're both n digits long. So I have this number in my head, right? I have this number that I've written down, x, and then I increment it. How long does it take to increment an n-digit number? Just shout it out. N, right? Worst case n. I might get lucky, right? I might not have any carries. If I don't have any carries, it's constant time. Right? But worst case scenario, it takes me n time steps to increment an n-digit number. And how many times do I do that increment? I do it y times, right? So the time is at most, there are y increments, and each one takes me n time. If I want an answer that only is a function of n, right? Right here I have y and I have n. Let's say I want to understand the runtime in terms of the size of the input. The size of the input is n, or 2n, because these are n-digit numbers. The size is 2n digits, n for x, n for y, right? If I want to understand the runtime in terms of the size of the input, in terms of n, well, what can I say? I can say that in the worst case, what would make this the slowest? What could y be that makes it the slowest? Basically, the largest n-digit number there is, which is 99999 n times, which is roughly 10 to the n. So this is at most 10 to the n times n. Okay? So the runtime of algorithm 1 is certainly at most 10 to the n times n. If you're a little more careful and track the carries, because this is very pessimistic. This is like I'm always carrying all the time. Most of the time, I'm not going to carry all the way to the end. And if you're more careful about reasoning about that, you can show that, in fact, the runtime is more like 10 to the n. You don't really need the extra factor of n. But 10 to the n is already pretty bad. Right? This says to add two 10-digit numbers takes 10 to the 10 times 10, so 10 to the 11 time. That's 100 billion. 100 billion time steps to add two 10-digit numbers. That's terrible. Okay? So this is a correct algorithm. And by the way, for this class, I want you to, maybe this is also the order of importance in algorithm design, okay? So it's very easy to get a very efficient algorithm that's not correct, right? Return 0. That's very fast, okay? So first, just try to get an algorithm that's correct, okay? It doesn't have to be fancy. It doesn't have to be clever. And then once you have something that works, then think about how to do it faster. Okay? And I would say that's a good way of thinking beyond CS170 when you got into the world, too. Many times, you don't actually need the fanciest, fastest algorithm to do your job. Maybe n actually is 5 for the problem you're trying to solve, and then who cares what you do? Okay? But this is a correct algorithm, but it's not that fast as n gets not even that big. But luckily, we all know another algorithm. And this is the algorithm that we all learn in, kindergarten, or I don't know when people learn addition these days. And the algorithm is you just write one number on top of the other. And you work your way from right to left, and you keep track of carries, right? We all know this algorithm. I'm not going to explain exactly how it works. And there you have your answer. What's the runtime of this algorithm? N, right? You do n steps. Okay. So a good thing to think about when you're designing algorithms is always, can I do better? Right? So we had this algorithm that took 10 to the n steps. Now we have another algorithm that takes only n steps. That's way better. Is there maybe an algorithm that only takes square root of n steps, or log n steps, or something that's much less than n? Okay. So anyone think that? Anyone have a reason for why maybe there isn't an algorithm that's better? Yeah. Yeah, so you said you have to read in the two integers, which takes time n. That's true, and that matters. So the point is, if there's a digit I didn't bother to read, like every digit matters. Right? There are some problems where not every part of the input matters, And then it's like, so what if I didn't read the whole input? But for addition, every digit matters. And if there's a digit I didn't read, then let's say I didn't read this digit. Well, if it was a 0 versus a 1 versus a 2, etc., the answer would be different. And since I didn't read it, I'm only going to output one of those things, or maybe something else. So I'm not going to be correct on all those possibilities. Right? And even if, yes?
But what if you just transformed your number into like base 10,000, so you only add one digit every time?
Okay, good. I'll get to that. I'll repeat your question and get to that. Okay, good. So here's the thing. Let me just address that now. So his question was, okay, I wrote things in base 10, right? Why don't I just write things in base 10,000? Then the numbers get shorter, then I'm faster. Even better, why don't I write things down in like base n? Okay, so then the numbers are extremely short. Okay, why don't I write them in base root n? Then they're only 2 digits long. Okay. So the problem with that is implicit in this is, first of all, I want to have what's called a uniform algorithm, right? What that means is that the code doesn't change. No matter what, if the input's 1,000 digits long versus 100,000 digits long versus 1,000,000 digits long, it's the same code that's actually running, right? So that code is going to work in some fixed way. Now, I could still pick a very large base in that code. Like instead of base 10, I could write that code to do base 10,000 addition. Even then, there's a trade-off in basically the size of the code, right? Because implicit here is that I've memorized how to add two digits that are each between 0 and 9, right? That's hard-coded somewhere in my program. I could do things in a bigger base, but then I would have to hard code in that program basically a bigger lookup table. And that would increase the memory complexity of my code. But yeah, even if I did write, like if I'm actually given a string of digits as my input, or 2 strings of digits as my input, even that conversion into that string into like some other base representation, I have to scan the string, which still takes n time anyway. So. Any other questions? Yeah.
Can you optimize if you had, if you had, say, like a power of 10, could you optimize using something like that? That would reduce your runtime as well.
You mean, like, can I have special cases where if I notice that my number is special, like it's a 1 followed by all zeros, then I can do less work? Yeah, but even to notice that I'm in that special case, I would need to read the input, which takes linear time. So, right. Anyway, you cannot, here's an even more convincing answer maybe, or it's equally convincing. Even if I magically knew the answer, right? Even if God came down and told me this is the answer, just writing it down takes linear time because the output has n digits, right? So, yeah. Okay. Yeah. The answer is you can't because n is a lower bound. But okay, but let's hear it. What? I don't know anything about computer architecture that would let you do it in less than linear time. In your computer, you can operate on machine words in like a single, let's say, cycle, or a constant number of cycles. And your machine word might be 32 bits or 64 bits. So you can add numbers that are, say, 32 bits long in constant time. But again, that's just working over a bigger base. You're not going to be able to get an algorithm that runs faster than something proportional to n for n-digit numbers in general. Okay. So let's move away from addition. Addition is pretty simple, and kind of the algorithm we all learned in kindergarten is the best you can do. Let's move to multiplication. So again, there are many algorithms here. Algorithm 1 is add in x, y times. So start with 0 and just keep adding x to your counter and do that y times. How long does it take to add x to your running counter? Your running counter is always going to be between 0 and the final product. Right? The final product is not going to be more than 2 n digits long. If you multiply an n-digit number and an n-digit number, the answer is at most 2 n digits long. So you have this counter that's at most roughly n digits. You're adding in x, which is n digits. How long does it take to add 2 n-digit numbers? N time. Right? So each one of those additions takes n time, and then you're doing it y times. So the time here is basically y times n, which we know is, again, at most 10 to the n times n. Okay? So that's the correct algorithm. It works. That's not the algorithm we usually use. The algorithm we usually use, I don't know, you learn at some point in elementary school. And that one works as follows, right? 5143 times 291. You start with the right digit, you multiply through, then you go to the next digit, you multiply through, and then you add it all together. And then you add it, and then you add through, right? We all know this algorithm as well. What's the runtime of this algorithm? Okay. It's some constant times n squared. So down below here you have, let's pretend there's a 0 here. So these are 2 n-digit numbers. I have to multiply this digit by n different digits up here. That takes n time. I have to do it again. That takes n time. Maybe a little bit more than n because there are carries. At most 2n time because of adding in the carries, etc. And then I have to add this down here as well, which takes another amount of time proportional to n. So total time here is, let's say, at most, I don't know. I don't want to keep track of all the constants, but it's certainly at most 50 times n squared time. Which I'm going to, some intro notation, I'm going to call big O of n squared, and we'll get to exactly what that means soon. Okay. For now, you can think of big O as just like hiding constants that I don't feel like keeping track of because I'm lazy. Okay. And a natural question then is, can you go faster? Right? So you could say, well, I have to read the input. Yeah, but the input's only 2 n digits long, so that doesn't explain why it takes n squared time. Again, the output's almost at most 2 n digits long. So even if you knew the answer, just writing down the output should only take 2 n time. Should it really take n squared time? And I mean, mathematicians like to make conjectures all the time, and usually the way it works is a bunch of really smart people worked on this problem for a really long time. No one could solve it. So conjecture, like you can't do better, right? Or conjecture, like a bunch of people tried to disprove x. They couldn't disprove x. So conjecture, x is actually true, right? That's how mathematicians work. Now, people have been multiplying numbers for a very, very, very long time, okay? And this guy is a Russian mathematician, probabilist, Kolmogorov. Okay. Well, he's known for many things. One of them is probability, but he's known for a lot of other things as well. He looked at the state of affairs, and he said, humankind has been multiplying for thousands of years. There have been lots of smart humans over this course of time. None of them have done better than n squared, or else I would have heard about it. Okay. So I'll just do what mathematicians usually do. I'll conjecture that the reason that they haven't found a faster algorithm is because there isn't one. Okay? So he believed that there was no algorithm faster than n squared. And he told that to other mathematicians in his circle in 1960, which is not that long ago, right? I mean, okay, you all are younger than me, but many of you, either your parents or like probably your grandparents were alive in 1960. It's not that long ago. Okay? He said in 1960 to his colleagues, conjecture, you cannot multiply 2 n-digit numbers faster than some constant times n squared. Now go home and prove it. Okay? And I think he thought that this was going to be, taken care of. Someone would prove that he's right. You can't. He was proven wrong. Someone actually came up with an algorithm faster than n squared. And let's try and understand how that works. So, algorithm 3. Here's the idea. I'm going to look at those numbers. Five, 1. Is this chalk very visible? I feel like it's not coming out great. Let me try another one. Which is better, the 5 or the 4? They're the same. The 5. The 4. They both suck. Okay. I'm not sure I can fix the both suck thing, but oh wait. Oh, I think that's better. Okay. So there's x. Here's y. What I say? 0, 2, 9, 1. This is a paradigm that we're going to talk about more in the next 2 lectures. We're going to use a paradigm called divide and conquer. Here's what I'm going to do. I'm going to take the first half of these digits, the second half of the digits, and then do the same thing for y. And I'm going to label these things. This here is y high, the high order digits, and this is y low. And similarly for x. This is x low, and this is x high. So what am I saying here? I'm saying that x is equal to 51, which is x high, times 10 squared, which is 10 to the n over 2, right? So 51 times 10 squared is 5100. And just make sure the 51 comes to the left enough. Plus x low. And y is equal to y high times 10 to the n over 2 plus y low. And I think when I was a kid, they taught us about the distributive law of multiplication over addition. What does that mean? That means that x times y is equal to x high, y high times 10 to the n over 2 plus n over 2 is 10 to the n, plus x low, y high plus x high, y low times 10 to the n over 2 plus x low, y low. Okay. So let me write this as a times here. That's not very pretty. Okay. So I have some recursion. In order to multiply two n-over-digit numbers, x and y are n-digit numbers, I need to recursively multiply two n-over-2-digit numbers, right? And how many times do I have to do it? I have to do it 4 times. 1, 2, 3, 4. Right? And whenever you write recursive code, you need to have a base case. Otherwise, you just recurse forever. And the base case is your multiplication tables. Right? That's why your teachers make you memorize your multiplication tables. Okay? When you get down to, say, 1-digit numbers, you know the answer by heart because you have it in your lookup table in your brain. Of course, once you multiply them, you also have to do some more work, like multiplying by 10 to the n. But going back to what someone said earlier, that's easy, right? Certain numbers are easy. Multiplying by 10 to the n just means you add n zeros at the end. You need to do another add n over 2 zeros. That's also easy. And you also need to do some additions. You need to do an addition here, here, and here. But we know that addition is easy. Addition is only n steps, not n squared steps. So that's easy. So what we know at the end of the day is that the runtime to multiply two n-digit numbers. Oh, wait, this was the bad chalk. Or was it? So let T of n be the runtime to multiply two n-digit numbers. That's at most, what's the runtime to multiply two n over 2-digit numbers? Because that's what we have to do, 4 times. And then once we have that, we have to do the other work, like adding some zeros in, doing some additions, etc. That takes at most some constant times n times, n time, right? That's if n is bigger than 1. If n is equal to 1, it takes, let's say, 1 unit of time. Because multiplication tables. Or 2 units of time, because it may be a 2-digit number, and we have to write it down. So, we have this function t of n, but what is it? Like, algorithm, we had 10 to the n over there, or 10 to the n times n over there, or sorry, over here, 10 to the n times n. We had n squared. Is this, we had n for addition. So what is this thing? Is this thing like n squared? Is it like 10 to the n? Is it like log n, root n? What is it? Okay. So let's try and understand what it is. Who thinks it's better than n squared? Who thinks it's worse than n squared? Who thinks it's n squared? Okay, we'll find out. So first of all, let me clean up a few issues that I've been sweeping under the rug. These were nice, so these are 4-digit numbers. When I recurse, I get 2-digit numbers. When I recurse again, I get 1-digit numbers, and then I'm done because I'm in the base case, right? What if I started with 5-digit numbers? Then if I try and split it in half, one is going to be 3, one's going to be 2, right? And, it's kind of weird. I'm just going to assume right now that the number of digits n is a perfect power of 2. That might not be the case, right? They could be 5-digit numbers. What's an easy kind of cop-out fix if they're actually 5-digit numbers? But I want to assume that they're actually powers of 2. Yeah, just keep putting zeros on the left until it is a power of 2. So a 5-digit number now is an 8-digit number. It just has 3 zeros at the beginning. Okay? And that only changes n by at most a factor of 2. Right? And we're ignoring these factors of 2 and 50, et cetera, anyway, so that's fine. So let's try and understand the runtime. So up here, at the top level of recursion, we have these 2 n-digit numbers. And the time it takes to multiply those 2 n-digit numbers, so basically the total time is the time from the 4 recursive calls plus another cn time to combine those results. So I'm going to write cn here. So that's the amount of time it takes to combine the answers from down here. How much was I doing from down here? These are multiplying 2 n over 2-digit numbers. How long does it take to multiply 2 n over 2-digit numbers? Well, c times n over 2. N is now n over 2, right? So c times n over 2 plus 4 times t of n over 4. So c times n over 2, and then there's 4 down here, and this is going to be c times n over 4, etc., until I get down to basically the base cases, the base case where it just takes 1 unit of time because it's in my multiplication table. So the total time I spend is just add up all these boxes. So this is cn over 2, this is also cn over 2, etc. So let's try and do that. So the time per level of this recursion tree, well, this level, the root level, it takes me cn time. The next level, it takes me cn over 2, but 4 times, right? There are 4 boxes here, 4 recursive calls. So that's 4 times c times n over 2, which is also known as 2 times cn. And then down here, how many boxes do I have? 4 squared. Because each of these 4 boxes gives me 4 more boxes. So there are 4 squared boxes. Each one costs me c times n over 4, which is 4cn. And then there's a pattern here. The next one is going to be 8cn, etc. So at the level j, it's like 2 to the j times cn. Good. So what's the total time? The total is, well, there's Cn in all of this. So let me factor that out. Cn times 1 plus 2 plus 4, plus 2 squared plus 2 cubed plus plus 2 to the k. Where k is basically how deep is this tree before I get down to the base case. So how deep is the tree? Log n? Log base what? Log base 2 of n, right? I'm done when 2 to the k, well, the number of digits has to be at most 1. So when n over 2 to the k is equal to 1, I'm done. So if you move things over, this means that n is equal to 2 to the k, which means that k is equal to log base 2 of n. Okay. Now, what is this sum? In case you're rusty on this, if you define a sum S to be, say, 1 plus p squared plus plus p to the k, then p times s is p plus p squared plus p cubed plus p to the k plus 1. So this is p plus p squared plus plus p to the k plus 1. So that implies that ps minus s, which is also known as s times p minus 1, is the difference of these two things. But all of these cancel. So that's p to the k plus 1 minus 1. Right? Which means that s equal to p to the k plus 1 minus 1 over p minus 1. As long as p is not equal to 1, because you're not allowed to divide by 0. For us, p is not 1. For us, p is 2. Okay. So now we're almost done. Our total time is c times n times p is 2, k is log n. So 2 to the log base 2 of n plus 1 minus 1 over 2 minus 1. 2 to the log n is n. 2 to the 1 is 2. So this is like 2n minus 1 over 1. So this is Cn times 2n minus 1, which is big O of n squared. Okay, so we did all that work. Exactly, thank you. We did all that work, and we got nothing. And in fact, it's not just big O of n squared. It's what I'll call theta of n squared. So I'm just sneaking some more notation on you until finally it all becomes second nature. So big O is sort of, I'll formally define this soon. Big O is sort of like less than or equal to, right? Big O is like it's at most n squared. Theta is sort of like equality, sort of. I'll define it soon. It's like it's not just at most n squared. It really is n squared. It's some constant times n squared with some lower order term because you subtract Cn, but Cn is much smaller than n squared. So it's a more complicated version of what you learned in grade school. In fact, it's going to be slower. It's going to be slower than what you learned in grade school, right? Because doing recursion costs time. You have to like actually push parameters on the call stack, and like you're doing all this work really for nothing. Okay? So this was a total waste of time. Except one of Kolmogorov's friends figured out how to save it. So let me tell you how he saved it. Actually, I'm going to leave that up there. And this is going to be magic. Actually, you know what? Let me do the following thing. Let me leave the T of n here. Let me do it here. So here's his trick. So we need 4 products, right? We need this one. We need this one. And it seems like we need these 2. Okay? Now, this guy, Kolmogorov's friend, realized, wait, I don't actually need these 2 products, because at the end of the day, I'm just going to add them. So really what I need is their sum. I don't actually need each number individually. Is there a way I can get their sum without getting each one individually? And he was inspired by a trick of Gauss to quickly multiply complex numbers, which I'm not going to show you, but I'll just show you directly what he did. He said, okay, look, I'm going to do 3 recursions instead of 4. The first recursion is going to be xh times yh. That's my first recursion. My next recursion, B, is going to be x low plus y low. Okay, that's another one. So this is B. That's A. Oh, what? Oh, times. Okay, and the next one I'm going to do, I'm already using C. Let's call it D. D is going to be x high plus x low times y high plus y low. Which is a really weird thing to do, right? What am I saying? I'm saying I'm going to take 51 and 43 and add them together. I'm going to take 2 and 91 and add them together. And then I'm going to multiply those 2 numbers. I mean, it has nothing to do with anything. Okay? But what's the magic? The magic is this is just A. This is B. And the sum, you can verify this if you want, the sum is D minus A minus B. Right? Because if you multiply out D, you do get the terms you want. You get x high, y low, which you want. You get x low, y high, which you want. But then you get 2 other terms that you don't want. But those terms you don't want, you know, because you recursively computed them, so you just subtract them off. Okay? And subtraction, addition is linear time, so is subtraction. I mean, subtraction is almost the same algorithm as addition. So you can do the subtraction quickly, too. So now, I get a new recurrence, which is not 4 times t of n over 2, but it's 3 times t of n over 2. And now what does that change up here? So, yes, I still, it still takes me, maybe C is different now. It's not the same C, because I have to do some subtractions. There's some extra stuff I got to do there. I have to do this addition here, 2 additions. But there's some other constant C times n that it takes to combine the results. But now I don't have 4 children. I only have 3 children. This child is gone. Yeah, someone said awe. Yeah. That's life. So you have 3 children. Each one of these children is also an n over 2 digit number. So it takes c times n over 2 digits to multiply them. Then I recurse down to 3 children again. 3 children again. 3 children. So the tree looks very similar. It's just 3 instead of 4. So this 4 is not a 4. It's a 3. This 4, there are 3 children here. There are 9 nodes at this level because each one of these 3 itself has 3 children. So this is 3 squared, etc. So this is not 2cn. It's 3 halves cn. And this is not 4cn. It's 3 halves squared cn. And this is 3 halves cubed cn. Okay. So now, all these 2's are 3 halves. Okay. What's k now? I'm branching by 3 and not 4. What's the new k? How deep before I get to the base case? What? Just shout it out. Log base 3 of n. It's log base 2 of n. The k doesn't change, right? Because log base 2 of n. Because what is, basically, I'm still going from n digits to n over 2 to n over 4 to n over 8. I'm still halving the digits each time. So the time it takes to get down to 1 digit is the same. The only thing that's changing is that I'm having less children along the way. Okay? Instead of branching out 4 times, each time I'm branching out 3 times. But I'm still going just as deep. Not any deeper, not any shallower. So I had that formula which said that, if you remember, that sum s is p to the k plus 1 minus 1 over p minus 1. So let's try and figure out what that is now. Okay, so Cn times, so p minus 1 is 3 halves minus 1. P is 3 halves now. And then I'm doing 3 halves to the log base 2 of n plus 1 minus 1. Let me just drop the minus 1, because the runtime is at most, if I drop the minus 1, the runtime is certainly at most that. That minus 1 is really just getting in my way. I mean, it's just annoying. So it really is a minus 1 here, but it's upper bounded by not having the minus 1. 3 halves minus 1 is 1 half. If you divide by 1 half, that's the same thing as multiplying by 2. So this is the same thing as, 2cn times 3 halves to the log base 2 of n times 3 halves to the 1, which is just 3 halves. 3 halves to the 1, so let me just put that out here, times 3 halves to the 1, which is 3 halves. So the 2's cancel. So 3cn times 3 halves to the log base 2 of n. What's 2 to the log base 2 of n? Shout it out. Don't be shy. N. 2 to the log base 2 of n is n. So I divide by n, but there's an n here. So that n cancels with that 2. So at the end of the day, this is 3c, which is just some other constant, times 3 to the log base 2 of n. Wow, this chalk is getting on my nerves. There we go. Yes. That's what I like to see. Okay, good. Okay. Now, 3 is also known as 2 to the log 3. Okay. So, let me give myself some space. So this is, I said, 3c times 3 to the log base 2 of n. This is the same thing as 3c times 3 is the same thing as 2 to the log 3. 2 to the log base 2 of 3 to the log base 2 of n. You know, a to the b to the c is the same thing as a to the bc, which is the same thing as a to the c to the b, right? Yeah. So let's do that. I can basically just switch the order and take log base 2 of n first. 2 to the log base 2 of n is n. This is 3c times n to the log base 2 of 3. Magic. Okay. Now, is this better than n squared? Yes. You don't need a calculator to know that, because log base 2 of 4 is 2. So log base 2 of 3 is something. It's some number. It's definitely less than 2. Okay. In fact, it's roughly 1.585. So this is roughly up to a constant. So let's say, well, this is certainly big O of n to the 1.585 something. Strictly better than n squared. And you might ask yourself, okay, this is good. I found this to be very surprising when I first learned it, because like everybody's been multiplying for a really long time, and you know, I just felt like I actually felt like I was lied to in my childhood. Seriously, I mean, my teachers told me about the n squared algorithm. You would think they should at least like mention that this algorithm exists, like maybe there's something better out there. They never mentioned it. I had to wait until I was a college student to find out that basically my whole childhood was a lie. Okay. But you know, I was able to continue my life. So you might ask, does anyone ever actually use this? That would be a good question. I actually didn't know the answer myself. Okay, that's enough. Okay. I didn't know the answer myself. But I did know. Anyone here ever code in Python? Anyone code in Python? Anyone never code in Python? Okay. Looks like almost everyone. So if you haven't coded in Python, but let's say you've coded in C or Java or C++ or whatever, one nice thing about Python is that it does kind of arbitrarily long precision arithmetic. Okay? So you can have like, you know, ints in C are 32 bits, right? If you have and longs are, say, like, you know, the size of your pointer, which is like 64 bits. Longs in Python can be arbitrarily long. Just think of like an arbitrarily long string of digits. Okay? So n could get very, very big. I mean, Java has, you know, big int that's implemented in the standard library. But in Python, it's really, you don't even have to use the big int. It's just standard ints. They just don't overflow. It's great. Okay? So I wondered, well, someone who created Python, what's this guy, Guido? I forgot who created Python. I think he was working at Google at some point, and then Dropbox stole him, if I remember correctly. Do you know what I'm talking about? Okay. I think Guido, maybe I'm pronouncing his name wrong. What? Okay, I believe you. I trust you.
I'm his son.
Okay, you're his son. Oh, are you? Oh. I don't trust you anymore. He's a liar. Okay, good. So, whoever wrote, you know, the library for Python to kind of implement everything in the back end, they had to run into this. So I wondered, like, what is their code doing to multiply integers? So I did what anyone would do, which is I just downloaded the Python source code. Okay. So let's now see what it does. So I found out that it's an object, and then there's this thing called longObject, longObject.c. It's magic. Oh, I forgot to say what this algorithm is called. Did I say what this algorithm is called? It's called Karatsuba's algorithm, because the guy's his last name was Karatsuba. Okay. And how do you spell Karatsuba? Well, the source code will tell us because it's in the Python source code. So the Python source code actually multiplies integers using this algorithm that I just showed you, this wacko recursive algorithm. But if you read it a little more carefully, what does it say? For int multiplication, use the n-squared school algorithm, meaning the one we all learned in elementary school, unless both operands contain more than Karatsuba cutoff digits. Karatsuba cutoff is 70. Okay? So if the numbers are less than 70 digits long, use the algorithm we all know from elementary school. Otherwise, use Karatsuba's fancier kind of divide and conquer recursive algorithm. Why, okay, so any guesses? Like why? This is real, right? This is not, no one's pranking me here. This is actually the Python source code. Why would they do that? Why would they say, if n is less than 70, use the slower algorithm, and if n is bigger than 70, use the complicated algorithm? Yeah. Yeah, because Karatsuba has higher constant factors. That's right, right? The point is, like, there is a cost, again, as I mentioned before, there is a cost to using recursion, right? You have to, like, push parameters on the stack, right? There's an actual cost there, and pop off. And, you know, the standard kind of iterated for loop algorithm has a much smaller constant factor in front, right? So yes, it's n squared, but, like, which is faster? Kind of, is n squared faster? Or is 50 times n faster? Well, it depends on what n is, right? If n is less than 50, 50 times n is less than n squared. If n is bigger than 50, 50 times n is better than n squared, right? So that's basically what's going on here. I don't know what experiments they ran, but they implemented the code. They ran some experiments on some machines, and they were like, well, we've observed that if n is bigger than 70, then you should actually use the more complicated algorithm. So there you have it. That's what Python does. So this is real stuff. Why would anyone ever multiply 70-digit numbers? Just like, you know, for maybe your third grade. Third grade is when I think you're supposed to learn multiplication tables. Maybe it's earlier. But, you know, as the grades continue, math gets harder and harder. And maybe in 7th grade, you finally have to multiply 70-digit numbers, right? Is that how it works? No. No one ever does that. But there are people, not people, but mostly computers, that do multiply 70-digit numbers, or actually even 1,000-digit numbers. And anyone ever use like HTTPS? You go to https.amazon.com, basically secure browsing. Okay. So behind the scenes there is something called public key cryptography, and kind of the standard schemes to get that lock in your browser, you know, URL buffer there, to get the security. They do multiply very big numbers together. Okay. So if you take some class where you cover cryptography, you'll learn more about that. I'm not going to cover that today. Okay. So anyway, you've learned about Karatsuba's algorithm. Maybe I'll write it down. I mean, it's in the book, but for today, Karatsuba. When I first learned the name, I don't know why, I guessed that Karatsuba was actually from Japan. It sounds like a very Japanese name. It's not. He's Russian. Okay. But what's a natural thing to ask? So we know that there's the n-squared algorithm. We now learned that there's an n to the 1.585 algorithm. You are now professional algorithmists. That's why you're taking this class. What should you be asking next? Can you do better? Yeah, exactly. Can you do better? Okay. So, people, you're not the only one to ask that question. Okay, so can you do better? And how might I do better? So one natural guess might be, Karatsuba breaks the numbers into two parts, right? And then does some wacky thing to get 3 multiplications recursively instead of 4. And that's where the savings comes from. Instead of breaking it into 2 parts, why don't I break it into 3 parts, or 4 parts, or 5 parts, right? Why don't I go crazy? K parts, okay? So n parts, they're n-digit numbers, right? So now each part only has 1 digit. Okay, so that's a little too crazy. But Tomb and Cook, basically, Tomb in 1963, and Cook in 66. So it's amazing, right? Like thousands of years, there's been no progress. Karatsuba has this very nice algorithm, and then like within a couple of years, all of a sudden everybody's jumping on the bandwagon. Okay? So, not jumping on the bandwagon, but this is like how real progress happens in research. Someone makes a breakthrough, and then people realize they can build upon that. So basically, you can do something like O of n to the log base 5 of 3. Is that right? No, that's a little too... That's less than 1. Forget that. What you can do is n to the log base 3 of 5. Yeah. So there is a way to actually break up your numbers into 3 parts each instead of 2 parts, and only have to do 5 recursions instead of... I guess the naive thing would be doing 9 recursions. Okay. Right? Because basically when you do the distributive law, you have a sum of 3 things, a sum of 3 things. You distributely multiply. You have 3 times 3, 9 recursive products. So you can actually get away with only 5, and then you get log base 3 of 5. And more generally, you can do big O of n to the log base k of 2k minus 1 for any constant k. So I can break it up into 10 parts and get n to the log base 10 of 19. Okay. Now, remember these big O's are hiding constants, like 5 or 10 or 50. There is a constant here that depends on k. You could say, like, why don't I just jack up k to be something really big so that log base k of 2k is basically 1. But there is some constant here that kind of explodes as you increase k. So you can't just increase k for free. And then in 1971, there was an algorithm by Schoenhagen and Strawson that was O of n log n log n. Now, what's the base? What are the bases of these logs? It actually doesn't matter because we saw it earlier. Log base a of n is the same thing as log base b of n over log base b of a, right? And log base b, if a and b are constants, like log base 2 versus log base 10 or something, this is just some number. It's just a constant. So kind of big O doesn't really care what the base of the log is, as long as it's a constant. All constants are the same. So n log n. And I don't want to delve into this too much, but basically, just a show of hands, who's heard of like polynomial interpolation? Who's heard of that? Oh. Okay, who has not heard of polynomial interpolation? Don't be shy. Okay, some people have not heard about it, right? So basically, if you have a degree d polynomial, there are ways to like uniquely specify it. One is tell me what are the coefficients of the polynomial. The other is evaluate the polynomial at a bunch of points, and it turns out if you evaluate it on enough points, it uniquely specifies the polynomial. Okay. Right? Like 2 points specify a line. 3 points specify a parabola. Okay. So maybe you've heard that. Okay. In general, d plus 1 points specify a degree d polynomial. So Tu and Cook, kind of this algorithm here, was basically using that approach. What they said is that an integer is really a polynomial evaluated at the number 10, right? Like, let's say I have 5, 4, 3, 1. That's the same thing as p of 10, where p of x is equal to 1 times x plus 3 times x squared plus 4 times x cubed. Or, 1 times x to the 0, x to the 1, x squared, plus 5 times x cubed. Right? So 5, 4, 3, 1. So there's a polynomial here, and if you evaluate it at 10, you get the number. Okay? So kind of the whole idea between what I'm saying now, I'm just saying for your own benefit. Okay? We're not going to quiz you on this. The basic idea here was I have these 2 numbers that I want to multiply together. It's the same thing as I have these 2 polynomials I want to multiply together. But I don't actually want the product polynomial. I just want to know what's the product polynomial when you evaluate it at 10. Okay? And what they said is, if you divide up the numbers into, instead of 2 parts, you divide it into k parts each, then you have a polynomial of degree k minus 1. Because each part is like a coefficient in the polynomial. Okay? And they said, let me then, and what's the product polynomial? If you have 2 degree k minus 1 polynomials, the product polynomial has degree at most 2k minus 2. So it's uniquely specified by its evaluation at 2k minus 1 points. That's why there's a 2k minus 1 here. Okay. And then they just kind of pick some small numbers to evaluate it at and then do stuff, and then they interpolate. And the interpolation is like solving a linear system. So I'm just saying stuff. It's okay if you don't get everything I'm saying. But the idea here was to use polynomial interpolation. And the idea here is to use something that you're going to learn soon called, in a future lecture, called the fast Fourier transform. And really, the fast Fourier transform really at its heart is polynomial interpolation, but kind of done at some very specially chosen points such that you can do the interpolation more quickly. And if you choose those points very carefully, you can basically think of this as like that algorithm where k is log n, but evaluated at some very specifically chosen points to make the interpolation fast. Okay? That might not make sense now. It will later when we talk about the fast Fourier transform. Anyway, that was Schoenhager and Strawson. And that was like the world record for a very long time until this guy, Martin Führer, is still alive. He's at Penn State. In 2007, what he got was basically n times log n times something like, I think, 8 to the log star of n. Have people heard of log star? No? Log star is the number of times you have to take log base 2 to get down to 1. Right? So what do I mean by that? Log star of 2 is 1. I just have to take log of this once to get down to 1. Log star of 2 to the 2 is 2. If I take log of this once, I get 2. If I take log of it again, I get 1. Log star of 2 to the 2 to the 2 to the 2 to the 2 is 5. What is this number? 2 to the 2 is 4. 2 to the 4 is 16. 2 to the 16 is 65,536. Right? I know you've all memorized your powers of 2. 2 to the 65,536 is, I'm not a physicist, but I hear it's more than the number of particles in the universe. Okay? So if you take log star of the number of particles in the universe, in fact, something that's way bigger, you get 5. So for all practical purposes, log star of n is always at most 5. Okay? But in reality, it does go to infinity. It just goes to infinity really, 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 really slowly. Okay? So this is like almost n log n, except there's this 8 to the 5 here, basically. Okay. There were a couple papers afterward that showed how to improve this 8 to a 4. So only 4 to the log star n. And only very recently, Harvey and, what's his last name? Van der Hoeven. In 2019, so you might not have been alive when this was happening. You're all alive in 2019, okay? I think. I know some geniuses get into college very young, but not that young. So O of n log n. Okay? Yeah. I know. I didn't do it. They did it. But to me, you're living in a very exciting time in history, right? Where while you were, I don't know, any freshmen in here? A couple freshmen. Most of you are not freshmen. There are some freshmen. While you all were in college, or maybe your senior year of high school, or wherever you were before here, community college, wherever, someone figured out finally how to get n log n for integer multiplication. Integer multiplication is one of the first algorithms you learn in your childhood, right? Everyone knows integer multiplication. And there are some loose reasons to believe that there is no faster algorithm. We don't actually know that. There could be a linear time algorithm. Okay, but there are other conjectures that people have linked to this problem. Like if you could do faster than n log n for this, you could do better things for like network coding, which is some other problem that people have thought about for a very long time. But people have thought about integer multiplication for a very long time too. So maybe that's not a very convincing argument. But n log n was like the holy grail since Schoenhagen-Strassen. Okay, people like Schoenhagen-Strassen were like, if we can finally get n log n, we'll feel like we've achieved our goal, and it's been done very recently. So very exciting times. We have 5 minutes left. What I am going to do, I'll give you a sneak preview of the next lecture or two. So this was what's called a divide and conquer algorithm, right? Because we divided the input into parts, and then I guess we conquered the parts. Yeah, okay, good, right? So it turns out that this paradigm is useful for other things, like people have probably heard of merge sort, maybe not. So that's a very useful paradigm. And then I also want to talk about something that you're all familiar with. So I mentioned, all right, I'm almost done, guys. I'm almost done. Guys and gals and everyone else. Everyone. So I mentioned that even this way of writing down the input using like Arabic numerals was, popularized first by Al-Khwarizmi, later even more so by Fibonacci, or further west by Fibonacci. And Fibonacci is also, people have heard of Fibonacci numbers probably from 61A, right? So there are different ways to compute Fibonacci numbers, and all of it boils down to like adding and or multiplying. So I'm going to show you next time many different algorithms for computing the nth Fibonacci number. And as we're going to see, it's going to turn out that you basically, to do it as quickly as we know how to do, you're going to rely on fast integer multiplication like Karatsuba or like the Harvey van der Hoeven algorithm, etc. Okay? So, questions? Okay. You're released.